All right, guys, this lesson is about the remainder theorem. And basically, the remainder theorem is just this. That's why it's in a big, bold font. When you use the zero of the divisors in input, the output is the remainder. Okay, that may be like a foreign language to you right now, but we're going to talk about it today and hopefully you understand it better. So I'm going to focus on input and output. Okay, when you have a function, all right, so a function where it's f of x, when we're used to x and y, okay, where x is the input. So when it's in function notation, instead of y as an output, we're going to use f of x as an output. Okay, so if we substitute a number for x, if we input a number for x, the value that we get, the f of x, is the output. Okay, I didn't mean to draw a line through a remainder there. I was just trying to draw that line. Input, output, like a table. X is input, f of x is the output. All right, so exercise 1, it says, basically, we have a function p of x. Instead of f of x, they're calling it p of x, and we're dividing it by a binomial. Okay, they're calling the binomial that we're dividing by, or the divisor, x minus a. It says to first simplify the division using polynomial long division, and then evaluate p of a. Okay, so we've practiced long division. You should pause the video and do long division on your own. But basically, we're going to do long division here. This is how we set it up. And we all know that we want to multiply this x by something to get the x squared. So we distribute. When x squared minus 2x. We're careful with our subtraction. This is negative 8 minus a negative 2. So it's the same as negative 8 plus 2, which is a negative 6x. And we have the plus 18. And then this would have to be a negative 6. Okay. In order, or when we distribute that, it'll give us a negative 6x plus 12. I'm kind of going faster this because we've already learned long division and practiced long division. All right, and 18 minus 12 would give me a remainder of 6. Okay, so I'd write my solution, or my answer. My quotient is x minus 6, and then I have a remainder of 6, and I put it over the divisor of x minus 2. All right, so the remainder theorem does a couple neat things for us. It actually helps us to check our answer of long division. Okay, this is my long division solution. Okay, and now I'm going to use the 0 of the divisor as an input for my function p of x, and the output represents the remainder. Okay, so first of all, we're going to go over the 0 of the divisor. Okay, so the x minus 2 is our divisor, right? So x minus 2 in this case is our divisor. I'm just going to label some stuff here. X minus 2 is the divisor. And apologize for this messy handwriting. Okay, so the 0 of the divisor is basically what we get, what number we'd have to substitute for x to turn this into a 0. Okay, we're used to zeros of factors when we're solving quadratics and we want to find the 0 of the factor. We basically just set this equal to 0 and we would solve. So x equals 2 is going to be my 0. Okay, so I'm going to use the 0 of my divisor. I'm going to use x equals 2, and I'm going to substitute. I'm going to put that in for my input of the function p of x. All right, and so that's what this is. That's what p of 2 is. All right, so I'm going to, instead of an input of general x, I'm going to plug in the 0 of my divisor. Okay, so I'm going to substitute a 2 every time I see, and really I should put parentheses around these. Anytime I substitute something. And when I evaluate this, all right, you can type this whole thing into your calculator, or you can use order of operations. This would be 4 minus 16 plus 18. and that would be the same thing as negative 12 plus 18, which is a 6. All right, so this is my input. I'm just going to set it up like a table. In this case, I used P of X. Okay, I don't like how it drags that little extra piece. Okay, so when I used the 0 of my divisor, my output was 6. All right, so this is the remainder. And that's what I got over here, right? The remainder was 6, so that's a check. Okay, so basically, whatever function we're dividing into, okay, if we take the 0 of the divisor and insert it as an input, we should get the remainder. That's what the remainder theorem is. Okay, so another one. Okay, we're going to, again, use long division, so I suggest you pause the video and do the long division on your own. Just move this down. All right, so this would be x. I get my x squared minus 7x. And I'm going to subtract it. Again, I have a negative 2 minus a negative, so I can turn that to a positive. I'll bring down my 5x. Okay, this would have to be a plus 5. And I'm going to distribute. I get 5x minus 35, and then I'm going to subtract. And again, I have a negative 25 minus a negative, so it's going to turn into a positive. And it looks like my remainder is 10. Okay, so the quotient of this, I have my x plus 5 plus my remainder of 10 over my divisor of x minus 7. All right, so this appears to be my answer. Okay, I'm feeling pretty confident. I think I do pretty well with long division. But if I really want to check my answer, I can use the remainder theorem. All right, so this is my function. Okay, you notice it says P of X is my function here. And they're getting 7. Okay, we're using 7 as the input because 7 is the 0 of my divisor. So just to review vocabulary again, the divisor in my problem was x minus 7. The 0 of that divisor, okay, I'm not going to do the work now, it's just whatever value will turn this into 0, would be a positive 7. Okay, should be consistent there. All right, so if I use the 0 as my input, okay, so 7's my new input, I'm going to replace my x's with a specific input of 7, and I should get an output that's the same as the remainder 10 here. Okay, so this is 49 minus 14 minus 25, and that would be, I can put my two negatives together, that's negative 39, and 49 minus 39 is 10. So I'll just carry this down. All right, so it's a check for my long division. Okay, so when I substitute the 0 of the divisor, the output is the remainder of the division problem. Okay. Okay, so exercise 2, it says use long division to determine if x plus 3 is a factor. Okay, so this is super specific. If something is a factor, okay, if something is a factor, then it divides evenly into the function, okay, and basically the remainder is 0. All right, so factors, by definition, they divide evenly into a polynomial. Okay, so if it's a factor, put a period there, then the remainder will equal 0. Or we can say that there's there's no remainder. Okay, so a factor by definition will divide something evenly. That means there's no remainder at all. Okay, so it says use long division to determine if x plus 3 is a factor of this, and then check by using the remainder theorem. All right, so we're going to do our long division. I'm going to try to divide x plus 3 into this 2x squared plus 11x plus 11. All right, so I'm going to have to start with a 2x here to get my matching 2x squared. 2x times 3 would give me a 6x here. I subtract. That's going to give me 5x plus 11. This would have to be a plus 5 to multiply by x to get that first term to match. And then 5 times 3 is 15. And when I subtract 11 minus 15 is negative 4. Oops. So 11 minus 15 is negative 4. All right, so this actually has a remainder of negative 4. Okay, if I wanted to write my solution, I'd write my quotient of 2x plus 5, and I could put minus 4 over x plus 3. Okay, so the first answer to the first question is this x plus 3 is not a factor of 2x squared plus 11x plus 11. Okay, so right here, x plus 3 is not a factor of 2x squared plus 11x plus 11. Okay, and the reason why it's not a factor is because it has a remainder other than 0. Okay, so it's not a factor because the remainder is not equal to 0. Okay, all right. And it says use the remainder theorem to check. So, well, hopefully you're catching on with the remainder theorem. In order to do the remainder theorem, we take the 0 of the divisor. So we want the 0 of the divisor. And in this case, the divisor is x plus 3. So the 0 divisor in this case would be a negative 3. And the function that we divided into, okay, it doesn't name the function. It doesn't say p of x or f of x or anything. It just tells us the trinomial. So I'm going to call it f of x just because I can. It's not listed as a specific function. So if I use the 0 of my divisor as an input, and evaluate this, okay, make sure you're using order of operations, or you can just type this whole thing into a scientific calculator, but I would have to do exponents first, so this would be 2 times 9. Okay, 2 times 9 plus, I can multiply these, that would give me negative 33 or just minus 33 plus 11. So that would be 18 minus 33 plus 11. Then I could do 18 and 11. That's 29 minus 33, and that is negative 4. So this f of negative 3 is negative 4, and that's a check because that's the same remainder I got when I did long division. Okay, so if they asked me if x plus 3 is a factor of this, I don't even have to do the long division. I could just go straight to here to see if the remainder is 0, because it's only a factor if the remainder is 0. So I could have just used the remainder theorem if they did not ask me to do the long division piece. Okay, so on the next page, this next page of notes, all right, they're giving us, instead of giving us an equation for a function, they're giving us a graph of a function. All right, so this graph is p of x. All right, so this is another way to do it, because a graph just has an infinite number of points. So each point is an input and an output. And when we're using the remainder theorem, okay, the input is always the zero of the divisor. Should probably zoom in more often to make my handwriting neater. And the output is going to represent the remainder. Okay, so we want to keep this in mind. We don't have to have an equation. We could use a graph or we can use a table, which we're going to use in the next example. All right, so it says, what is the remainder when this function p of x is divided by x plus 4? Well, if we're dividing it by this is my divisor, okay? It's being divided by this, so that means this is my divisor. So the input is going to be the zero of that divisor. Okay, so we're going to have different scenarios. So the zero to the divisor would be -4. Okay, now instead of substituting -4 into a equation that I don't have, this is -4 is just my x value. So I go to the x value of -1, 2, 3, -4 right here. Okay, that's my x value of -4. And the y value just happens to be 0, right? The y value is 0. It's on the x-axis. So it says, what's the remainder when this function is being divided by x plus 4? So for this one, the remainder is 0. Okay, so it's asking, is x plus 4 a factor? Well, yes, because the remainder is 0. Okay. Okay, and then it asks us another question. What's the remainder when p of x is divided by x plus 2? All right, so now that they're giving us a new divisor to use to test out. All right, so this is a new scenario. The divisor of the factor x plus 2, the zero of the factor x plus 2 would be -2. And again, the zero of the divisor represents our x value. So I'm going to the table or the graph where the x value is -2. Well, I have to go up to this point, and this coordinate is -2, 4. Okay, and we could have labeled this, I guess, 2 as -4, 0. So when x is -2, when my input is -2, then output is remainder. So in this case, the remainder is 4. Okay, so it's asking me, is x plus 2 a factor? Well, no, because the remainder is not equal to 0. Okay, so you can only have a factor if the remainder is equal to 0. Okay, otherwise it's not considered a factor. Factors divide evenly with no remainder. All right, and then I told you, besides using an equation or a graph, we can also use a table. So now this is an example where they use a table. All right, and again, I'm going to keep repeating this. The input is always the zero of the divisor. And the output represents the remainder. Okay, so we can actually look at our table right now, and we don't see any factors because I see no remainders. Okay, I see no remainders that are equal to 0, so I don't see any factors listed. Okay, so it says, what is the remainder when q of x is divided by x minus 2? Well, again, if I'm dividing by something, that means this is the divisor, and the zero of the divisor for this one, the zero would be a positive 2. So I'm going to look at my chart, and I see a positive 2. When I substitute a positive 2 or use it as an input, the remainder is 3. Okay, so it doesn't ask me what the remainder is. It just jumps to the question, is x minus 2 a factor of qx? Well, I can say no. Okay. Explain how you arrive at your answer, because the remainder is equal to 3, and you can just notate that the remainder is not equal to 0. Okay. If something is a factor, the remainder must be equal to 0. And it's as simple as that. Okay, so just to reiterate, okay, maybe this makes more sense to you now, this main sentence that describes this lab. When you use the 0 of the divisor as an input, the output is the remainder. Okay, so you use the remainder theorem to check your answer to long division. Okay, that's what we did here. We did the long division. We had a remainder of 6. We substituted the 0 of the divisor, which is a positive 2, and we got the remainder. So we knew our long division was correct. We did that for the second problem as well. Okay, we talked about in order for something to qualify as a factor, it has to have a remainder of 0. And we're not only limited to equations, we can use graphs and tables to use the remainder theorem, because it's just an input-output relationship. All right, we're going to do 2 more examples together. And on this page, we're going to do exercise 3 and exercise 5. Okay, so exercise 3 I want to do with you just because it's kind of confusing. There's so much notation. Okay, so it says by definition, basically a binomial is a factor of a function. Okay, if we get a quotient. Notice this quotient has no remainder. There's no plus r over the divisor. Okay, and it just says qx is another polynomial. What must be true of the remainder p of a for x minus a to be a factor of p of x? Well, this is that fact again. Okay, so the remainder must be what in order for something to be a factor? And basically, the remainder, and actually, I'll write this out as a sentence since it's asking it. Okay. The remainder must equal 0 for x minus a. I should have zoomed in because my handwriting was horrible. For x minus a to be a factor of p of x. And it does say explain, so maybe I should add just some more of a statement. I apologize. You know what? I'm going to erase that and type it because it's really messy. Sorry about that. I should use the text boxes more often. All right, I guess it's good to reiterate this because it's a very important concept. All right, so, all right, the remainder must equal 0 in order for x minus a to be a factor of p of x. Factors divide evenly into a polynomial. All right, so again, that concept, in order to be a factor, you must have the remainder of 0. All right, the last problem we're going to do is exercise 5. And again, this concept comes back. Okay, so we see that keyword factor. It says for what value of k, change my colors here, for what value of k, so we're solving for this value, will x minus 4 be a factor of this polynomial? Show how you arrived at your answer. Well, as soon as you see that we need to factor, we know that the remainder has to equal 0. Okay, so we have this function, and I'm going to call it f of x. I could call it p of x, I could call it q of x, I could call it really anything I wanted. Okay, we have this function, and I need the remainder to be 0 when I have a divisor of x minus 4. And you should probably pause the video and see if you can figure this out on your own without my help. Hopefully you gave it a shot. But remember, we have this function, and we have enough information to get the input, and we know the output. So what we're going to do is, okay, we know that we want the 0 of the divisor. Okay, the 0 of the divisor in this case is a positive 4. And if it's a factor, we have to have an output of 0. Okay, so that's what we're going to do. We're going to substitute our output of 0, and we're going to substitute our input of 4, and then we'll just have one variable left, which is k. So k times 4, I'm just going to write 4k instead of k4, just because it looks better. And then minus 52. So now, and I should have expected that, because if I'm solving for k, I can only have a single variable. So I have 16 plus 4k minus 52. And then I can combine like terms. And I'm going to write my 4k first. And a negative 52 and a positive 16 gives me negative 36. Okay. And I'm going to take it over here. I'm going to add 36 to both sides to get 36 equals 4k. And when I divide by 4, 9 equals k. So my final answer is k would have to equal 9. All right, so your homework for this section, okay, your homework is just to do exercise 2. Okay, this is multiple choice. Make sure you're showing work for credit, and you're going to do all 4 pieces of exercise 4. Okay, these are all just practicing your remainder theorem. You can use your notes and have fun.